Okay, now we're going to learn how to do, I hope, learn how to do a good job of looking at examples in our textbook. When you look at this example in the textbook, there we go. It's such a long problem. Let's get this up a little bit more. Okay, I can't get it too high. There we go. Right there. Okay, when I get this guy and I look at it, it will make more sense to me if I do what I'm going to show you right now. I'm going to cover up that right-hand page. Okay, so I can't even see it. Let's see, my right-hand page is all covered up. And I'm just focusing on one thing now. I want to look at the problem itself. And I want to digest that and see if I can understand what it is that they're asking. And then, as I go down to the first little section of what they're doing, which is the given and the find, I will have a better understanding of what it is that I'm looking at. And that is called, in the book, they call that analyzing the problem. So let's go ahead and go back to the smartboard. Ooh, that's fun. That's hydrogen peroxide, by the way. H2O2. Yes, HO. Yes, definitely. Yeah, this is full size, the manpower type molecule, right? Okay, so let's go into here and look now at what we're dealing with. What I would like to do, and those of you watching on video right now, would you please stop the recording and then come back up after I give instructions. For all of you in the classroom, get out your cell phones. The first person to identify or get the uses and information on succinic acid, the first one will get an extra credit point. Okay, our student is now going to read the definition that he found on the internet. And if you're at home watching the video, do the same. Find it, see how your find compares with his find. Go for it.
Rather than a definition, it's more of the formula though. The
Whatever you
formula
want.
is C4H6O4. It's a water-soluble colorless crystal with an acid taste that is used as a chemical intermediate in medicine.
C4H6 what?
O4.
O4. Okay, there it is. Now, what would the empirical formula be for this guy? What would you divide by? C2H3O2. So this is the molecular formula, and the empirical formula is easy to find. What's the value of N? 2. Sure, because that's what we divided all the subscripts by. Yes. Oh, tell me, more uses. Yes, uses. Tell me more about it. Here, come on up a little closer. Okay, another student found more on succinic acid. Go for it.
It's used as a medicine for joint pain.
For joint pain. Oh, I'll have to tell my wife about this one. This is great. What else can we use it for?
That's all.
That's all you found? Okay, do we have anything else?
It's used in the food and beverage industry.
Ooh, what are they putting this stuff in?
I don't know.
What do they say?
Primarily as I don't know how to say this.
What?
Acidity regulator.
An acidity regulator. Very good. Yes. That's it? Okay, good. Now that we know a little bit about it, let's look at it up close here. Here we go. Let's get this guy nice and big for you. Okay, so this is succinic acid as a powder. And how would we make this into a solution? Mix it with what? Yeah, sure. Mix it with water. It's very soluble in water. And that's how it becomes succinic acid. Right now, it's just the molecule. And so it's not acting as an acid. Okay? Here, let's look at it structurally. Oops. There we go. Here it is structurally. And succinic acid is, you're seeing all the different parts of the succinic acid molecule. So we've looked at the molecule here, and let's tuck that back away. And here it is, succinic acid, and the formula format that we would use when we're doing organic chemistry. So we have not done any organic chemistry yet, but this is common in organic chemistry. And can you? All right, right here, 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 here. Those represent carbon atoms. And you can see that up here. 1, 2, 3, 4 carbon atoms. And here's where our OH group is. An OH group on an organic molecule like this is going to give you an acid. That's how we tell acids. And so these hydrogens will ionize a little bit and form a weakly acidic solution. Okay? So that's a little bit about succinic acid. It's kind of nice to know what it is and be able to know more than just, oh, we take succinic acid and we do this, this, and this, and then we get all of this, and wow, isn't that wonderful? Well, it's not so wonderful if you don't have any idea of what it is. So now I hope that succinic acid has become a little bit more friendly for you. Okay, now let's get this guy out of here and deleting. Come on, here, and delete, and there we go. Now, let's do given and find. As we read up here, we should be able to do given and find. And the given and find is where we are going to be able to look and see in a more organized way rather than just in sentences, which we see up here. Okay. Up here, we're just seeing the sentence, and it doesn't mean as much to your mind as when you see it like this down here. And you can see we're looking for the empirical formula because it said that right here. Are you all with me? The molecular formula, which it says right here, and then the percent by mass of each of the elements. Okay, and the percent by mass is 40, 5.08, and 54.24. But wait a minute. This says mass. But up here it says percent. Anybody catch that? Okay, it's different. If it's different, we need to understand why it's different. So let's do one little assumption. What do all of these percentages add up to? 40 plus 5.08 plus 54.24. What do you think? 100. Okay, let me explain how we solve problems of this nature where we're dealing with mass percent. Since it is mass percent, why not call it grams? But how many grams do I have? That's the question, right? So they make the assumption, we're going to assume that we have 100 grams. Now, let's look at the percentage. The percent says up here that we have carbon. So here's carbon. The percent of 100 grams would be 40.68, would it not? Yeah. Okay. And the percent of 5.08 would turn into grams as well. And so as we're going back through this and looking at it, we're going to change all of these guys into grams. And let me get my little pointer. Where'd my pointer go? Inside the blue? Where is that? Ah, it's hiding. Oh, that little stinker, it was hiding. Okay. So, okay, here's our example, and. Okay, so maybe we better change this arrow to a red. So, we made our arrow into a yellow, and now we can see here that we are changing the grams now. Once we've made this assumption, if we assume 100 grams, then these percentages will also be grams, won't they? Okay, so that makes this part very easy to understand. You want to put this in your notes. This is step number one. Step number one is changing from the percentage into grams and multiplying it by the molar mass to convert to moles. So this is converting to moles. Why do we need moles? Why are moles such a big deal in this particular problem? And let's get this down now. We don't need to look at that anymore. Okay, because we've got that stuff all down now. Okay. Why are we converting to moles? And let's see. Ashley?
Not here.
Not here. Okay, Hannah's not here. And Eddie, what do you think? Why do we want to convert to moles? What virtue is there in that?
So, reason why we convert from moles so you cross out grams?
Oh no. Well, we're going to cross out grams right over here. These crossouts are because we took the molar mass off the chart for carbon and we converted it into moles. But when we're in moles, what is the virtue of being in moles? No, we have mass. Okay, I'd like you all to open up your textbooks. Now, what do you see in all of the formulas here? Where are the numbers?
There's subscripts.
Huh? Where are the numbers? What do you see all the numbers as? Subscripts. Great. Okay, these subscripts are important because these subscripts, like right here for the zinc chloride, that tells us we have 2 chlorides and 1 zinc in the molecule, right? Okay, these can be called mole ratios because if we have 1 molecule, we would have 2 chlorines and 1 zinc. How about if we had a mole of zinc chloride? Then how many chlorides would we have? Yes, 2 moles. And how many moles of the zinc would we have? Did I say a mole? Or 2? Yeah, okay. Yeah, I was afraid I might have said 2 moles. Yes, but for 1 mole of the zinc chloride, we'd have 1 mole of zinc in there. Yeah. Okay. So what I wanted to make sure we are on track with that, because what we're going to be doing, what we're figuring out is a molecular formula, right? And that's where we're headed. And on top of the molecular formula, so right here where we have the moles, we have odd numbers, don't we? They're not odd, but they're not whole numbers, right? They're all fractional numbers. So the fact of what we've done here in step number 1, and that's what you want to write down, step 1 in the example problem on what page? What page is that on? Page 334. Okay? So if you're doing this at home with your textbook, I would like you to be sure and use 2 pieces of paper so you can see just 1 step at a time. It will help you understand and be able to use this step in your actual calculations that you're doing on your own. So succinic acid has this mole ratio, and here that little baby is. And let's make this guy a little wider and make it easier for us to see. There we go. And there. Okay, now we can see it really well. So we've got the carbon, hydrogen, oxygen ratio at 3.387 to 5.04 to 3.390. Yes, question? Because that's what we assume. The ratios stay the same whether we have 100 grams or whether we have 1 billion grams. Don't they? The ratios are still the same of the molecules inside. They're not going to change. Are you right? Are you with me? So, if we know that 40.68% of that molecule's weight, or of the moles of the molecule, whatever number of grams we have, because this is all done by mass, right? It's percent by mass. So whether we weigh 100 grams or whether we weigh 1,000 grams or 1,000,000,000 grams, it's still going to be that percent. Okay? If I choose 100, that's why I'm assuming 100, and we use this commonly to solve these kinds of problems. If I use 100 grams, it makes it possible for me to just take out the percent sign and plug in the grams. You don't have any calculation at all to do. It's simple. That's why they do it that way. Does that make sense? Yeah. Okay, good. So now we've got a problem. What is our problem in using these for subscripts? They are not whole numbers. And all subscripts that we saw in all of those equations, and by the way, I was in the textbook on what page? Oh, anyway, it doesn't matter that much. You look at any number of equations anywhere in any textbook, you'll always find whole numbers. Okay? So let's go down and let's cover this little guy back up. And now let's focus on step number 2. Do you see what that does to your mind when I cover that up? It just lets you focus on the thing that you're doing right now. So, Cindy here? No. Yes. Okay. Cindy, would you please tell us, what do you think we're doing here? What do you think we're doing with all this stuff here? Where do you think that 3.87 right here? Where did I get that? Yes, the smallest value. Okay, that's what they're after here. So, what are we doing? We're getting the simplest ratio by subscripts, or to get subscripts to whole numbers only. And we started with the smallest value. See, this guy was 3.387. This guy's 3.390. This guy is 5.040. So this is the smallest. Okay? That makes this guy 1 mole. And happily, it also made this guy into 1 mole also. 1.001, you can round that to 1 with no worries at all. So these guys are just right on nice whole numbers. But this guy's the fly in the ointment. So, Cindy, what do you think we should do? What could we multiply this by to make it a whole number? Huh? Yes, very good. And what would the number become? Multiplied by 2. It would become 3. Now, can I leave my 1 mole here and my 1 mole here as 1? Remember, these are at a set ratio. When you make this 3, do you change the ratio? What's the ratio before you multiply this guy by 2? Come on. 1 to... Come on. 1 to 1.5 to 1. Right. That's what they're trying to show you right down here. See? 1 to 1.5 to 1. And that's where we end for that second section. Has everybody got this down? Thanks. Okay, this was number 2. We're going to go on down to our third section here. And in that third section, oh, look. There's the 2 that Cindy came up with. Okay, you see it? Right there. And we're going to multiply this guy by 2. We got to multiply this guy by 2 and multiply this guy by 2. And by doing that, by multiplying them all by the same number, we wind up with the ratio being preserved. And so we're multiplying the smallest number possible, 2, because if we multiplied by 1, it wouldn't do anything, would it? Now, the question came up last period. Yes, go.
Why can't you just say it's 131?
Because if you make it 131, it's not the same ratio you had to begin with. You've just changed the ratio. See, if I only multiply this guy by the 3, then I have a 1:3:1 ratio, which is very different from a 2:3:2 ratio. Okay? So anytime you multiply any of these guys by some number, all of them have to be multiplied by the same number. And that's what makes it so nice when you have these guys as whole numbers in the last section here. Now, let's get this back up so we can see this. We want to look back at this now. And you see these guys were 1 to 1.49 to 1. And you can't change this guy without changing these, or you'll have a different ratio. Yeah? It won't be 1 to 1.49. It'll be 1 to about roughly 3. And so now you're in hot water because you've messed up your formula. And you're trying to get it to whole numbers. Simplest ratio, subscripts, whole numbers only. That was step number 2. That's what we were all about there. Now let's go down to step number 3. When we did this, we multiplied by smallest number, and I probably ought to say here, multiply all by smallest numbers possible. And it still covers. Good. Okay. To get the empirical formula. Now, how do I get the molar mass of the empirical formula? What do I do? Huh? Okay. Well, I've got my ratios now, right? Okay. There's the empirical formula. That's what we just figured out here in this step. Okay. So we have our empirical formula, C2H3O2. Oh my gosh. That sounds like acetate, doesn't it?
Yeah.
CHO 232, huh? But that's the empirical formula. It's not acetate. Okay? So let's go on down and look at the next one. So everybody's got what was here in step 3? Okay, these guys, you want to use these when you're doing the next, the actual problem out of the textbook. So down here we go. Now, what are we doing here? Anna, not here. And Audrey. Yeah. Okay, Audrey? What are we doing here? Look. Look until you know. And nobody help her. She's going to learn something by doing this. Okay, would you say that one more time?
Converting to grams.
Yes. Okay, I stopped the recording until she got the idea of what was happening. We are converting moles here into grams using, what is this? Where did we get this number? Where did we get this number? Where did the number come from? Shh. Well, then think about it for a while. You want to say that again?
On the table.
Okay, periodic table, right? What do we call this number? It is the atomic number, also called the molar mass. It's the mass of 1 mole of the element. Okay? 1 mole is 6.02 times 10 to the 23rd, right? Of the atoms. Okay? And that many atoms will weigh 12.01 grams. Whether you're in California, Australia, South America, Central America, all the way up into Alaska, if you're at the bottom of the ocean or up in the sky.
What do you mean? But even the bottom of the ocean, like the pressure is like really.
So what? Carbon will still have the same mass. Yeah, we'll still have the same mass. That's amazing, isn't it, huh? Okay, now, in space it will still have the same mass. It won't have the same weight. Won't weigh anything, yeah, but it will have the same mass. Because it doesn't have a large body like an Earth to have gravity exerting force on it. You'll learn about that in physics if you take physics. Yeah. Anyway, so we've converted our moles into grams for the purpose of getting the molar mass of the what? Is this empirical or molecular? This is empirical formula. Now we're ready to do the next step. So, this is what you write down for step 4. Okay, would you all get that down? You're adding all the masses. Okay, once you convert the moles to masses, all the masses in the empirical formula. See, we're halfway home. We've got the empirical formula figured out. We did that up here in this last step. Okay, remember we had it up here? And now we're down in the next step, and we got the mass of each element, plus we added them all up to get the total mass for the molecule for the empirical formula, for 1 mole of the empirical formula molecules. Here, let's get this down. Okay, have you all got steps 1, 2, 3, and 4 down? Because that's going to be your guideline for getting the next part. So let's go on down here. Now, divide. Here we go. Let's put this back together. Yeah. All right. And now we're going to divide the experimentally determined molar mass, which we just added up, right? Okay. So we're dividing the experimentally determined molar mass of succinic acid by the mass of the empirical formula. Ah, what are we trying to find here? Why are we doing this, Alex? Why are we doing it? Don't help. And those of you watching at home, start thinking. Don't just stare at the screen. Alex, what are we trying to do here? Read it. Read it out loud. So what are we trying to do? Huh? There you go. That's what we're trying to do, the determine word. And you might want to put that in your journal when you see the word determine. That's going to be talking about the find. What's to find? Okay? I don't see you writing. You just got a little nugget of good information. Okay, here's what we did. Or here's what they did. Molar mass of succinic acid. Okay? And this is the molar mass of what? Is this the molecular or is this the empirical? This is the molecular formula. Did they give us that? That was part of the given. It was part of the given. Okay? Molar mass of the empirical formula. That's the guy that we just figured out. Everything we've done down to here was to get this guy. That's why you have to have a given and a find when you're solving these problems. Okay? Let's look at this now. Here's the number that we were given in the problem. Here's the number that we just figured out in this step up here. Okay, there it is. 59.04. See, as you're working these kinds of problems, as you're going through an example, you have to see where everything comes and goes. Otherwise, you're not going to get anything out of staring at the problem. It's just a whole bunch of numbers and words until you hook it up. Just 1 second. So when we multiply this n, which we figured out right here, by the, what is this called? Which formula is it? The empirical. We got the what formula? And that's it, folks. Now, I want you to start question number 59, or 52, is it? Yeah, 51. Go to question number 51, and you want to do this. Set up your problem side by side with the notes that you took before. You won't be able to pull over the blue circles. So because you can't pull over the blue circles, you'll have to do your own given and find for the problem up above. This is question 51. And then take it step by step exactly as you saw it when I did it in class or earlier in this video if you're watching the video. So here we go. We got to line these guys up, and we're able to go ahead and go one by one, figuring out all the steps according to the information that we just got by watching this video earlier, or took notes on as you were doing the video. And once these guys line up, you're ready to go, and you can check it piece by piece by piece. And you should be able to solve question number 51 now, and you've got everything you need to be able to make it work and understand.